Here's an exercise to show you how to check the composition of two functions is onto and one-to-one, and therefore is it invertible. Also, the product of two functions f and g, is it invertible, meaning that is it onto, is it one-to-one or not. So the two functions f and g are shown here. They are defined from the domain of R to the codomain of R, as you can see for both functions. The best thing we can do, given how busy f of x is just to simplify it, and that helps if it works. So f of x is equal to expand x squared plus 2x, that's an algebraic expansion, plus 1 minus x squared minus x plus 1. So x squared, that is canceling out the other x squared, and as a result you can see f of x simply becomes x plus 2. And this is much better than what seemingly looked like a complex function, sort of complicated function, which is not. It's just a linear function of x. For g of x, it's already super simple. So with that in mind, therefore, we can form f of g of x, which is simply composition of function, or basically f of g of x cascade function. So I am going to substitute g of x as the argument of f. Argument of f is this guy, so it becomes g of x plus 2. But then g of x is negative 2x. So I'm going to get negative 2x plus 2. That's it. This is the f of g. Let me use a different color so that it's clear. This is the f of g of x. It's a linear function, and for any linear function, it is known that it is both onto and one-to-one. I'm going to prove it after this step. So yes, it is onto or surjective, it is one-to-one or injective. As a result, since both conditions are satisfied, you would say it is invertible. Now, let's check the f product of f and g. Well, we just found that f is this simple x plus 2 function, and also for g, it's not difficult to see that it is just negative 2x. So let's multiply f times g of x, multiply negative 2x, compute the product of negative 2x and x plus 2. So what you get is negative 2x squared, and then negative 4x. Okay, so as you can see, now we are dealing with a function that has x squared in the function. So as a result, this function is not anymore one-to-one, is not anymore onto. One easy way to see this is factor out the negative 2 and write it, for example, this way, just for the illustration. So it becomes x plus 1 squared. If you try this, it will give you negative 2x squared and then negative 4x, but then it will give you negative 2, which you have to add plus 2. So why did I write it this way? Because it helps visualizing it better. So if you try this, what you're gonna get in terms of plotting, if I plot with different colors so that you can see, it is looking like this. It looks like, maybe I show it this way, it looks like on the x-axis I have x. When x equal to negative 1, I get 0 from the second order component, and then I get 2 for the output. So let's say this is the output. But then as soon as x is increased, let's say to 0, then we're going to hit a total value of 0. And then when x is negative 2, the same thing happens. So there you go. This is negative 1, this is negative 2, this is y-axis, and this is 0. And as x is increasing from this point on, let's say you set x equal to 1, then you're going to get 1 plus 1, 2 squared. It will give you 4. 4 times negative 2 is negative 8, and then it means it's going to just go down quickly. So let me just, so it's just gonna go down quickly so that when x is equal to 1, it will reach -6, and so on and so forth. So it looks like a sort of bell shape, and the peak value is 1. Obviously, you can see visually that this is not one-to-one, assuming the domain and codomain of real number that is given to us. So don't forget that always check the specific domain codomain given. So obviously, you can see if I have this line, it will cross the curve in 2 points, which means that you will end up with same value on y-axis for y value for the output of product of f and g if x is this much, or if x is this much, or if x is this much. So basically means that on the x-axis there are two different values of x that will give you same value for the product of f and g, which is a counterexample showing that this function is not one-to-one. So I can give you basically the best way to say it is always officially, in the sense that you would say f product of f and g is not one-to-one, is not one-to-one because counterexample, because of this counterexample. So I'm gonna just write it here. Because of this counterexample, what is that counterexample? Okay, it is this counterexample. As you see that f, when you set x equal to 0, you get, when you set x equal to, let's say, 0, you get 0 for the whole function. When you set x equal to -2, you get again 0 for, so what I'm trying to say is f product of f and g for 0 is equal to the product of f and g for -2. And since we are having two different x mapped to the same y value, y meaning f product of f and g, that is exactly the counterexample for the one-to-one scenario. You never, in the one-to-one scenario, you never want to end up with a situation that two different values of x are mapped to the same y. So two different value of x from the domain are mapped to the same value in the codomain. Therefore, this is not one-to-one for the reason illustrated by this counterexample. This counterexample is serving as a proof for you. Okay, so that's one case. And for onto, it's obvious as well. You can see that visually this function on the y-axis never goes above 2. Never. So you're not able to realize value of +3 at the output of this function. So for, I'm going to say it this way, f, by the way, for the proof we are done, because you just showed that f product of f and g is not one-to-one, is not injective. As soon as you showed that it is not one-to-one, the function is not invertible, because if the function, which is this function, supposed to be invertible, it requires that to be both one-to-one and onto. Since you just showed it is not one-to-one, we are done with respect to answering the question. The answer is f product of f and g is not invertible because it is not one-to-one. But let's continue and check the onto or surjective property. So we just said f product of f and g is not surjective or onto because, well, number 3 belongs to set of real numbers. So since the codomain of the product of f and g inherited from f and g is r, as is shown, any real number from codomain should be representable. We should be able to represent it as an image as a result of mapping. But the thing is, we are saying 3, while is a valid choice coming from the domain of codomain of real number, is not, we're not able to represent it. There is no way, because 3 belongs to R, but there is no X. So we don't have any X to, but there is no X such that if product G is equal to 3. That's how you say it. Basically, I just summarized the fact that the peak value of function, as you see here graphically, is 2. It cannot go above 2. So if you say you want 3 on the y-axis, this function can't get to that level on the y-axis. So it means no matter what you set the value of x as the argument, input argument for the product of f and g, product of f and g cannot give you 3. So therefore 3 is not a mappable number. It cannot be an image for the product of f and g. It means any number above 2 in the codomain is not mappable to. So therefore, there is a portion of the codomain that is not covered by the function product of f and g, therefore is not onto. So in summary, in this example, the f of g or the f of g of x or composition or cascade function is invertible because it is both onto and one-to-one, given the domain and codomain of real number and given the function we found. But for f product of f and g, given what we found, which is this outcome, this whole outcome, it is obviously not one-to-one, it is not onto, and therefore it is not invertible. I hope that this example is helpful in terms of reviewing what you need to do when these kind of questions about composition or product of two functions asked.